So we just like to take a look at median heap. You've already got the code for min heap from before. The first thing I would do if you haven't practiced it yet is to go into the code for min heap and just simplify it first. So I'm not expecting to work with generics here. You can work with int values. Um, Okay, that takes care of not needing to import anything. We don't have to try to create an array of generic types. We just have an int array for your min heap. And you can take a look at the rest of the code. You can remove a few of the methods that were there before. And if you really want to, you can print it. But keep in mind that tree traversal, it's not going to give you the elements in any kind of order. So yes, when you look at the first node, that's the smallest on a min heap, or the element in the array with index 1. Then when you go to print that first element, if it's pre-order traversal, then it would move on and you would recurse on the left child and then on the right child. And just a reminder with the index positions on your heap, so in the underlying array, you've got the left child calculated with I times 2 and the right child calculated with index I times 2 plus 1. And it's a bit of a simplification because we keep the smallest element at index position 1 rather than at index 0. The only other thing I would probably point out, I mean, going back to look at the other methods, it's the same as it was before. Just keep in mind, instead of compare to, I'm just doing less than and less than. Same with for add, if you do swim or percolate, you're doing less than while you iterate. So that's bring after you add a value in, it swims it up to the top of the heap if it's the smallest element that you've added. Okay, and then just keep in mind that we've got the set min method because the element at index 0. If I'm going to do this application, I'm going to assume that all the elements that I'm working with are not less than 0. So if I have things that are not negative, that's okay, and if I have 0, that's okay. So for the set min inside my main code, inside median heap, we'll get here in a second, I set the min to -1. If you did want to have values within your median heap that were negative as well, you could always do integer min value to have the smallest negative value. Remember, they're just putting this at element 0 in the underlying array, so that way it makes the sink and swim methods work properly and the build heap method work properly. Similar for max heap, it's just that instead of things, when you're doing the comparisons and looking at what's smaller, you'd flip the less than sign to a larger than sign. So the max heap is really just the same code. It's just the comparisons are swapped. So keep in mind, it's pretty straightforward what we do with the min heap and the max heap. I would not expect you to write the code for the min heap or the max heap on final exam. You could be assumed to have these if you go to write a median heap. Now, the other thing to keep in mind is I would not expect anybody for a question like this to sit down and write the whole data structure. I would really only, because we've practiced this, I would really only take a look at something like the add method and then talk about, okay, in a certain situation, there's one of the cases we could consider. and I'll go through and I'll describe these. So there is quite a lot going on to have to think about. You're going to split the data in half and keep one half in the min heap and the other half in the max heap. And if you're like me and you tend to get values swapped when you're trying to think of two things, and I've studied a lot of math, so you have to keep in mind that even though math is complex, you shouldn't shy away from trying to learn it because you're always going to be in a better position if you're trying rather than if you're not. And you'll find your weaknesses that way as well. If you tackle the problems that are really difficult, you'll start to understand the kinds of common mistakes only you would make, and because you're different from other people, right? So I found one of the advantages of studying mathematics is that I learned the kinds of mistakes I tend to make. So that way, when I'm working on a problem, I can always go back and double check that and make sure that I can correct it if I did make that mistake. So you get better. Um, we go into the add method. Really what we're doing is we're working with the min and the max heap, like described in the setup for the question. And then, of course, we want to keep track of how many elements we have inside our median heap. A couple of the methods are pretty much the exact same thing. So is it empty? That's not hard. You're just returning whether the size is equal to 0 or not. But I've got another method here called balanced because I need to do different things depending on whether there's the same number of elements stored in the min heap as there are in the max heap. If all I really want is to grab the element that's directly in the middle of my set of values, then it simplifies things a little bit to have it so that the min heap always has the extra value if there is one, and there's an odd number of values. We'll see the simplification in the remove method, but not the add method. So it makes things a little bit more difficult in the add method. Okay, we've got 3 cases to go through, and you just have to think through one at a time. Don't try to solve the entire problem all at once. So when we go to add our value into the median heap, we're going to see, and we're keeping this simpler, so we're not doubling the size of anything to try to grow to larger than what we're expecting. So keep in mind that when you go to create your median heap, there's only so large you're going to go. So for this test code to try to get comfortable with programming this, test.java, I just make my median heap have at most 40 elements, and then I'm only going to mess around with maybe having about 12 of them. And you could try adding more, you could play around with it a little bit more if you want. So the min heap, I'm going to have at most 20 elements there, and the max heap, I'm going to have at most 20 elements. Now, if you were asked to write the constructor, I'm not going to take marks off if you didn't create it so that it's perfectly split. Say if there's an odd size that we're going to have at most, so that the min heap always has the one extra element like I've done here, where you would do math.ceiling divided by 2. So that way there'd be room for the extra element if there was one. And then the floor would have maybe one less than the min. Now, if there's an even split, then they would both have the exact same size at most. Okay, so that's why I would want to use ceiling and floor. And then I'm setting the min and the max heap just to make sure that that's okay. So that way it sinks and swims properly in both data structures. Okay, going back to the add method. The first case I want to think of is if the median heap is empty currently. So there's no elements in either the min or the max heap. So because the min heap always grabs the extra one, I'm automatically just going to do min heap, add the value, and that's it. I'll break. And keep in mind, after all the cases, we're going to increase the size and return true. because we would have successfully added a value. The case where there's exactly one element in my median heap, this is where it starts to get a bit hairy and you have to keep track of what you're trying to do. So in the min heap, we want to place the larger half of the elements because the minimum among those will give us the median. Compared with the other half, the smaller half of elements are going to be stored in the max heap. Okay. What I would like to do then is take a look at the min heap and make sure that if the value I'm trying to add to it is larger than or equal to what would be the smallest out of the larger half of elements, then that means this value really should go into the min heap. But I've already got one in there, so I'm going to take out what's already in the min heap and put it into the max heap. So remember, the max heap is going to be keeping track of the smaller half of the elements for us. So because what was currently in the min heap will then be the smaller element, I will put it into the max heap, and I'll put the larger element into the min heap. So I know that can be quite a bit to try to keep track of in your head. If you have trouble imagining that in your mind, I would say practice on a piece of paper. Write down a small set of elements, like 3 or 4, as you go through these cases. And try to work through what the code is doing and convince yourself that this would be the correct way to have it manage. So that way when you go to remove, you're going to grab the median element out of your set. Okay, if the value we're trying to add ends up being smaller, then that's great. We don't have to remove what is already in the min heap, which holds a larger value. And I would place the smaller value already into the max heap, and we're good to go. And you break. One of the common mistakes people tend to make with switches like this is they forget the break statement for each case, because otherwise the flow of the code will go from one case and execute into the next case. Okay, lastly, we have the most complex case to deal with, and that's where if we have more than one element inside our median heap, then we're going to do two different things depending on whether there's an equal number of values in the min and the max heap. So I'm going to call balanced to check for that. And if we do have the same number in both of our heaps, then we're going to check similarly to how we did before, but we're going to take a look and compare against. If we've got the same number, we're expecting to throw it into, at best, just put it into the min heap, because that's what's going to take care of the extra element. So if we really are larger for the value we want to add than everything that's in the smaller half of elements in our max heap, then that's great. We can just put that larger value into our min heap, and we're fine, because the min heap has the one extra. Okay, otherwise, it's something that should go into the min heap, but that would make it unbalanced. And we really should be taking something from our max heap. We should remove it and add it into the min heap, because it could be something that's even smaller. And then I'll add that new value into the max heap. And then we've got the reverse situation where if we've got it unbalanced, it means we have one extra element in our min heap. So that means we're either going to equal things out right away. So the best thing we could do is if the value we're trying to add is smaller than everything in the min heap. And so it should go into the half of the elements that are smaller. So I immediately throw it into the max heap. And then otherwise, you have to juggle things a bit, and you remove this, what would be the smallest of the larger half of elements, and place that into the max heap, and then put the larger value into the min heap. And then after, you'd be balanced. Okay, so that is quite twisty to try to think through those cases and then from each one go through thinking from the first one to the last one. So again, it is worth your time on your own to step through the code, work through a few small examples on paper, and convince yourself of what's going on. The other way you could do it if you don't want to write it on paper is you could try to do the poor man's edit, and you could do print statements to try to see what's stored in each of the min heap and the max heap, and then the value you're trying to add in. And you'd want to try to write out a little bit of description for each of these cases and then each of the conditions that you're checking. So is it balanced or not? Just to keep track of reading your output and you don't get lost at what's going on. The remove is really easy because of the way that we're considering the median to be defined. We're always taking either the element that sits directly in the middle if we arrange them from smallest to largest. If there's an odd number of elements, you'd have one directly in the middle. And if there's an even number of elements, it just, by definition, to make the question a bit easier, I'm defining it so that you just grab the one that's to the left of the middle if you've got an even number of elements. And so that way, when you go to the element, what you're looking for, you're always going to grab the one from the min heap because they're either balanced or it has an extra one. And if after that you're not balanced, it means that you need to adjust things. So, excuse me, because the min heap is always going to have either the same as the max or one more, then you're going to balance it again by removing from the max heap and adding to the min heap. And then, of course, because you're removing, you reduce the size and return the value that you grabbed. That's the median. Okay, if you're just looking for a peek at the element, you do like we had with the min and max heaps, and you just take a look at them. But we've already got that method implemented in both of those other heaps. So it acts like a wrapper in this case, but only from the min heap, which is nice. When you go to print, if you want to do that, because we've already implemented a print in the min and max heap, you could do one after the other. And remember, you've got the smaller half of elements stored in the max heap. And even though it doesn't print the elements from smallest to largest, it tends to print the smaller values first. At least it would for... No, it wouldn't quite do that, would it? Because if I got the max heap, it would always want to try to print currently what's inside of it. You go to remove, or you go to traverse the tree, and at the top it's got the largest element. So from smallest to largest, but not quite, because when you go to observe the children and you're doing a pre-order traversal, you're not necessarily, because it's a heap, you're not necessarily going to get from largest to smallest, nor will you get from smallest to largest with the min heap. But you get something close to that. So maybe the print is not the greatest, but you can still see what's inside of them. You might try to play around with how you would print it, and you're always welcome to implement a different version for yourself. There is level order traversal. I never did demonstrate that during the semester because it's quite a bit more to try to deal with than it is to do pre-order, in-order, or post-order traversals. You could try to do it a little bit easier if you have another parameter that you pass in when you recurse to keep track of the level of what level are you in at the tree. So each time you go to recurse, you're going one level further down the tree. So you would do level +1 when you recurse. And that can help you keep track of everything that's in the same level, and that would make it much easier for you to figure out how to print a level order traversal. Okay, there's quite a lot in this question to have to think through, and then of course if you wanted to take a look at the test code, I've got a bunch of values. I even have a few repeat values to demonstrate to you that it can handle that. And then you go to compile and run. You get it. So we've got about 6 elements before the middle. 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 3, 4, 5. So do we have to the left? Maybe if I've got an error, I would have to debug it, right? So 3, 3, 3, 3. I want to always choose the one on the left, so I got to make sure that I'm not losing something somewhere. So if I've got an even number, I'm expecting it to take from the lower half. I should be grabbing 6. So let's debug it and find out. Okay, so this is where I learn about my own mistakes, right? So the one thing that I noticed throughout the semester is it's really tempting to want to program stuff, and then when you get it compiled, there's no more compiler errors, and then you go to do the output, and you look at the output, and not really check it, and just consider it to be done. You never really want to do that. You always want to scrutinize your own programs, make sure that they are functioning the way that they're supposed to, and then debug. So you have to go beyond just compiler errors, especially after second year with 251, and then you move on to third year and you're doing any kind of programming. You want to be able to make sure the code that you're writing is going to do what you need it to do. If I take a look at my output, so I'm just approaching this with the most straightforward way because this is a very small example. I'm just printing to check what's going on when I go to add a new element to my median heap. And then I take a look at it, and then I realize, okay, so I'm off by 1 in what I would like to do to grab the median. And I have everything working okay, and we've got it balanced. We would want to, if there's an odd number of elements, grab it from the min heap. But actually, when there's an equal number of elements, we want to grab it from the max heap. If we want to take it from the left. So I could be nice and I could change the definition for what we would want to consider to be the median. You could take the right element. And something like that, I would be like, okay, if you wrote that assumption down on the midterm, I would be fine with a definition that has to do with statistics, and it doesn't have to do with the definitions that we work with for data structures and algorithms. Stuff like that is totally fine. I want you to use your own brain and make your own decisions about things. Now, if you're going to look at the application for what you're trying to program, that decision should be justified in some way. So is it going to facilitate what it is you're trying to actually do to solve the problem? So for now, I'm going to not take the easy way out, and I would say, all right, well, if I want to take the median, it's not so simple then to just remove from the min heap, is it? So if it's not balanced, I would want to take from the min heap. But I can't necessarily I would do integer min value. Maybe as a sentinel, I'd have that just to indicate that something might have gone wrong. I'm not going to do any exceptions or try to handle cases where we're worried about anything other than working with integers right now. The other issue you might want to program for practice with the remove method is also checking whether the median heap is empty or not. So I might do that after too. Okay, if it is balanced, then we would want to grab it from the max heap. And we don't have to adjust the min heap then. It's got the one extra value. And you can return temp. Okay, let's take a look at whether that should correct things. We do have the median as 6 when it's balanced. That's good. Let's just do one more small test, and I would say I'm going to remove out of my example the largest value and do one more check. And we still get the median 6 because we've got 5 values to its left and 5 values to its right. So we should be good. We'll highlight that, yes. Okay, and the very last little thing I would want to do is maybe throw an error if it's empty. And I think we have that up here with add. So we would want something similar to this kind of error, but we're checking if it's empty. I would say heap is empty for the error message. So I'm not doing exceptions at all. I'm keeping it pretty simple example just by doing error. And then once we're done with that kind of programming, I would recommend that if you're going to do any larger projects where you're writing your own data structures, that you also write code to test things as you go through your project and you make progress. Then you'll always have those tests and you can execute them when you need to. And you'll learn about stuff like that in software engineering classes. I know we have OPME teach them quite often. And you learn how to manage everything better as you keep going. So again, I appreciate everyone's patience while you go through your practice. I hope you're practicing leet code. I might have maybe one more example. I'll probably do something with trees. And then I should probably be in my office. I'll post a schedule where you can drop in if you want to stop in to see me. I'll do it over Zoom because I realize the buses make it difficult for people to get to campus. So if you really need something, always remember that you can email me and set up a time, and I'm willing to meet you on Zoom. Okay, I hope things are going well. This one is much more substantial practice, I have to say, and you definitely want to have pieces of some kind of question like this if it's going to show up on the final exam. Right, and you also get to see you should be debugging as well.